So we'll wait for 2-3 minutes, let everyone join, and then we'll start the class. Okay. So good evening, everyone. Greetings of the day. We have seven. Okay. So I hope the participation increases midway. So today, um, so yeah. So let's start with the So greetings of the day. So I welcome you all to week three doubt clearing session for the course Smart Grids Basics to Advanced Technologies, being taken by Professor N.P. Padhy and Professor Premlata Jena from IIT Roorkee. I am Swastik Sharma. I am a PhD student at IIT Kanpur, and I am a TA for this course. So let me share my screen. Yeah. So last week we were discussing about various kinds of DRs that are available in smarter grids. So these DERs, so the main focus of these DRs is to improve the penetration of renewable energy resources, most of which are being found at the distribution side. Now, so that we reduce our reliance over these fossil fuel based generations. But as we went further, we discussed two main kinds of DRs, which were solar and wind. And we found out that they struggle with two things, that is uncertainty and variability, right? So both of these renewable energy resources are uncertain. That is, we can't predict how much power will be available at what time, and variable in nature. That means their injection to the grid varies with time. I mean that they don't constantly inject. They don't inject constant power to the grid. So that so to so now when we move ahead, we found that to be able to support the grid better, I mean to further increase the penetration in our energy mix, what we need to be able to firm their generation. Firming their generation means so that they are able to constantly, so that they are able to inject power to the grid at a constant level. So for that, when we started, we uh, yeah. So for that, when we started, we wanted some kind of a storage device so that when they are generating more, they can store it, and at a later point when they are generating less, we can inject power. So that's where the need for storage devices comes into picture. So these offer many advantages. First is their location flexibility. These can be installed at any place. I mean, we don't require a huge capital or a huge land for them, like in case of wind farm or solar generation. This can be incorporated at any point at the distribution side or the transmission side, and hence these are better able to form. They are better able to form the capacities over there, and they reduce the investment that is needed for transmission and distribution systems when because of these intermittent variable renewable energy resources. So that's where they come into picture. They force these I won't say the force. They help make this variable renewable generation a bit uh, predictable, which is unpredictable at first. This can lead to decarbonization, rapid decarbonization in the grid. What do we mean by decarbonization? It's that the reliance on fossil fuel based generations should be reduced. So for that, what they do is they are able to better. Just a second. I don't know why my screen went. Yeah. So they are better able to yeah. So they relieve this reliance on carbon based fossil fuels, so that it's good for our environment. They are greener. Second, power reinjection. That's what I meant by that. When generation is more, you can store the power and then re-inject it later time when the generation is a bit less. Third, for last aspect is controllability. We can't control variable renewable energy resources. Whatever they are generating, we are trying to feed it to the grid, right? But using these BESS, we can have a better controllability over the VREs, that is renewable energy resources. So how did it begin? It began in 1839 when we developed fuel cell. The fuel cell was is where Sir William Robert Grove, he mixed hydrogen and oxygen in the presence of an electrolyte and produced electricity in the water for the first time. Then we went on to make a lead acid battery, then a flywheel energy storage. In a flywheel, so it's a freely rotating body, which once given power, it continues rotation whenever the power is withdrawn as well. So, like for example, if you've seen the the let's say a swing table for a tailor, right? So that swing table, you have two these rollers which is attached to a pulley. One is a bigger one which is at the bottom of the table, and one is at the swing machine. So what it does is when the tailor pushes the leg support that's given for running the sewing machine, it transports power to the flywheel. So when it withdraws that power, when he stops pushing the leg support, the flywheel continues its motion for some period of time until the inertia gives up. So that's where it comes into picture. The flywheel stores energy as a kinetic energy by continuing rotation even when the force is withdrawn. Then we went on to make nickel cadmium batteries. Then we started with pumped hydro energy storage. That's what we were discussing at the end too last time. Pumped hydro storage are those energy storage mechanisms where you have where you can pump water back to the reservoir when the generation is more, so that it acts as a load, and when generation is less, it can run it through the turbine so as to produce power. But these generally take a lot of land space, so these are generally made at places which is far off to different to community based or residences. Then we started with superconducting magnetic energy storage. Then came compressed energy storage, where the so when air is compressed, it has pressure built inside of it, which can help in firing a piston, which can help result in energy production. Then came supercapacitors, which are large capacitors having an insulator between two conducting plates, where which this insulating material stores energy in the form of electric field. Then came lithium-ion battery, which are popular nowadays. And then a paper battery was discussed, but it's still in a concept stage where we haven't found a real use case as of now. So if we divide energy storage systems, we can divide it into four broader categories. That is, one is thermal energy storage, where we store energy in the form of heat, which is thermochemical energy storage. Then we have mechanical energy, where one is pumped hydro-based energy storage and the other is flywheel. Then came chemical energy storage, which is hydrogen energy storage, and then electrochemical, which is battery or flexible battery. So if we classify ESS, so there are similar classification could be made, where I have just explained, given an examples of various different kinds of devices. In mechanical, again, it's hydro, flywheel, or compressed air. Then it's lead acid, lithium batteries, flow batteries, sodium batteries, and zinc batteries. We'll discuss more about batteries at a later stage. I'm just giving you an brief overview of what are the different kinds of energy storage systems or mechanisms or mediums. Then came thermal, where you had sensible molten salt chilled water, then latent ice storage, thermochemical storage. Electrical, you have supercapacitor or superconducting magnetic energy storage. Then chemical came power to power and power to gas. So in India currently, as you can see, based on this map, this is a roadmap where India is currently headed to. So right now we have a very less amount of energy storage, which we are going to expand in the coming few years. So we want to have um, we want to form the places which currently have variable renewable energy penetration, such as J&K. It has a total rooftop solar of 1860 megawatts. So we want total ESS to be of 296. And then Chandigarh, Rajasthan, which currently has the highest number of solar rooftop, so we want it to have a higher number of solar rooftop. So we are projecting 5,000 and a total ESS of 795 or 1327 megawatt hour. So that's currently a roadmap which we haven't achieved yet, which we are far from achieving currently, because this ESS requires a lot of capital. So it's very capital intensive. You need a lot of capital, you need a lot of land, you need a lot of money, so that to be able to make the project come into fruition. So yeah, so this is why ESS was this is how ESS is projected, at least in India. You can go through this map. I have the citation is also added, so you can check for your states as well what is the projection of various solar rooftop and ESSs which will be needed. Now, as I've already explained why ESS is needed, let me get into a bit detail. So from a system operation perspective, what is happening is So when you have coal-based power plants, so yeah, yeah. So when you have coal-based power plants, so they have few limitations. One, their ramping rate is quite slow. What happened? Yeah, slower ramping rate. So what do I mean by ramping rate, right? So let me just okay. So you have this load curve, let's say. So you get an early morning peak. I'm talking about residential right now, and then you have a late evening peak. So you need to, if in order to maintain frequency, what you need is you need to maintain this load curve. You need to be able to follow this load curve exactly. So let's say if you're, I'm just giving a rough number, don't take it seriously. So let's say this is 150 megawatt and you need 500 megawatt here, right? So the total, let's say this is at 6 a.m. and this is at 2 a.m. So in 4 hours, you need a total generation shift of 350 megawatt. That is, you need 350 upon 4 megawatt per hour of ramping rate. So currently, coal-based plants have they have a ramping rate of, I guess, I'll just add approximately, I don't know the number by hand, 6% to 8% of their total power capacity in an hour. So this ramping rate is quite huge. So to be able to manage this is difficult from coal-based power plants, but it's easier from hydro-based power plants because hydro-based power plants, what you need? You have water at reservoirs, you just need it to feed it through piston to your turbine. So you can increase it quickly. So I remember if you remember the time, I guess during COVID first wave, 2020 March, when our honorable Prime Minister asked everyone to switch off the lights, right, during, I guess, at 8 a.m. or something. So, people predicted that it's going to cost a huge, it's going to be detrimental for our power grids because we won't be able to manage such a huge ramp because in a jiffy or in seconds our load will go down and then the load will go up as well because people will turn on their lights eventually, right? So what did they do? So the system operators in different places, NLDC, which is the Grid Controller of India Limited, formerly known as POSOCO, they asked all the RLDCs, which in turn asked the SLDCs to keep their hydropower at a minimum threshold so that when the time comes for proper ramping, they can just quickly enhance their ramping capability to be able to survive the whole dip and whole crest and peak. So how did they do that? They asked their coal-based power plants to supply the base load. So I don't know the exact number. Um, you can go ahead and search it on the internet. There is this article by Professor Ankit Singhal from IIT Delhi. He explained this beautifully. So what did they do? They asked all their coal-based power plants to supply the base loads and asked their renewable these sorry hydro-based power plants to give minimum amount of electricity, I guess, and to have a sufficient headroom. That is, if you are 900 megawatt producing power plant, just keep 50 or 100 so that you have the rest of the 800 to support the ramping needed for the huge load. So all the country had their hydro powers switch to a lower megawatt range so that they can power the grid quickly. So that's how we sustained that load. So that's where ramping is usually needed. So fortunately, we haven't yet reached the place where solar penetration is too wide, where we would need it frequently on a per day basis. But as you can see, I'll explain in the further slides. There is this case study for New England ISO. where they have beautifully explained how their load curve will go down and their ramping ability or the flexibility would be needed much more. So I'll explain it in my next few attempts. So we discussed flexible ramping. So you need flexible ramping. So you need to be able to adjust to the load curve so that your supply and demand balance be maintained fairly easily. Then you need frequency regulation. So if I know, so can anyone tell me? So I've explained this a lot of time. What is the effect of these two things on frequency? Does it go up or does it go down? Just tell me one thing. Can anyone do it? So if you want to do in the comment section, let me add numbers. This is 1 and this is 2, so that you can just say. Anyone? No one. Nothing in the chat as well. Okay. So when generation is greater than load, frequency increases, while if load is greater than generation, our frequency goes down. So to be able to maintain the frequency in the bandwidth, which is 49 to 95 to 50.1, we we want it to be able to maintain this frequency regulation so that if at all frequency goes below this bandwidth, we'll be able to sustain or regulate it in a very less amount of time. And then black start services. So I don't know if you know, but these coal-based power plants that are there in huge number in India, they take at least 24 hours to be able to come up to their rated power. Why? Because these are steam-based, right? You first need to make steam so that you are able to fire your turbines. So, so black start services, what do you mean by that? If let's say power goes down completely someplace, right? So to be able to quickly uh, come up to quickly power the whole area for restoration, you need to able to have some black start services. So these black start services are currently, these can only be offered by either hydro based power generation or your renewable generation if they are formed with battery energy storage. So all of these things become non-existent if you want to have BESS, or let's say just ESS, energy storage system. So now investment deferral. What do I mean by investment deferral? So energy shifting and capacity investment. So energy shifting is nothing but, let's say, let's say you this is of your load, right? So let's say here your load is less, right? But you could generate more. So if you generate more here, you can do what? You can save this power so that you are able to survive here when the peak is there. So what you do, you generate power at a lower level so that you are able to discharge it during peak hours. So energy shifting could easily be done from ESS and capacity investment deferral. So let's say you have a transmission line connecting two areas. I have to add one more. So let's say you have a transmission line connecting two areas. Let's say if I draw, I don't know if I do a very good. So let me give you an idea. So it's a two bus system. This is one, this is two. This is 250 megawatt only. And let's say it produces 250 is too much. Let's give it 25 megawatt. So let's say it's generating 25 because load is only at bus two and its need is 50 and another 25 megawatt is coming from here. So now this can generate only this can transfer the generator at bus one can only transfer 25 megawatt because the transmission capacity has a rating of 25 megawatt only for the load at bus two. Let's say this is the maximum this generator can support, and the generation now becomes 60. So generator one can power that, but for that you need to have another transmission line in this region to be able to transmit that amount of power so that this load could be sustained. Given that this cannot be done easily, and let's say in order to sustain this as well, you need to have you can also increase the capacity over here. Still, you need capacity, right? So what you do, you can easily connect BESS at any location. You don't require, too much land for it. So a BESS could come into this picture and just add 10 megawatts so that this load is sustained. So that's the, I should show it like this only because still I'm saying BESS, just consider it as ESS. So it's supplying 10 megawatt. So this 60 megawatt could be sustained. So you can defer capacity investment until the time you really require it, because transmission is very costly. It requires a lot of things which are not discussed right now: transformers, substations, etc. Then you have PV and wind generators. So if you have them, what we do. Let's say if there is lot of intermittencies. So this is a kind of a thing which has a negative connotation, right? So you won't want something which is intermittent or uncertain or variable in your energy mix, right? You would want it to be able to sustain on its own. So how would it do that? It can only do that if, let's say, it's formed better. So to be able to reduce its curtailment and increase its capacity, or from its capacity, you can do that. So what I meant by capacity, I hope you all capacity firming, I hope you all got it. It's a fairly easy term to say, that you are trying to make sure that it has a constant power output. And mini grids. So I hope you have this distinction between mini grids, microgrids. So microgrids are generally smaller, in the range of a few megawatts. I have no exact figure. I guess it's a 1 to 10 megawatt. Please check the internet, I guess. And then mini grids are bit more. They have a bit more capacity. I guess it's 25 to 50 for them. So do check this figure. I'm not completely positive. Check it. So not good with figures. I'm sorry. So yeah. So what do? You have for mini grids, even microgrids, you have diesel generators. So diesel generators, again, they are fossil fuel based generators. So you are trying to reduce your reliance on them, right? And you are in turn having them in your these mini grids, because they can sustain the load in islanded mode of operation. So to reduce their reliance, you can have uh, energy storage system. Okay, so that's where I told it's a frequency regulation, capacity firming, grid investment deferral, reduce RE curtailment, ancillary services such as black start services, frequency regulation, etc. You can all get this from energy storage system. So mostly right now, battery-based energy storage systems are in a big focus because of less land requirement, but they are still capital investment because battery is costly. So India currently has 37 megawatt hour of battery storage, but we know that we have ambitious targets of 400 gigawatt of solar, let's say, PV generation. So to be able to form that in a better way, we need BESS. So it requires 236 gigawatts of battery, and in addition to that, 27 gigawatt of pump storage. So let's see if we are able to meet this. But given that its capacity, this investment is huge, this would be a bit tough. So So I already talked about what are the different types. Hybrids are intermix of all of these different energy storage systems. So hybrid is it's a mix of both, so that you can get the best of two worlds. So so you have, let's say, so for battery energy storage system, BESS, or simply BSS, battery storage system. I'll so I hope you are not getting any disturbances, right? I am at home, so just give me a minute. Yeah, sorry. So. hmm, So for BESS, there are a few terminologies. One is energy density. Energy density is that how much of energy can be stored in that medium, in that battery. So generally, when I say medium, it's the kind of battery that we are using, such as lithium ion or lead acid. Then it's power density. Power density is how much of it can it supply faster. I mean, Uh, so when we are talking about battery, it's usually connotated with charging or discharging, right? So power density, generally high power density means it can charge and discharge fairly quickly. Response time, how much time does it take to respond to your control input? Let's say you want to increase, you want to charge now. So the response time is this. You can immediately, with the switch of a button, you can just charge it. Cycle life. So this is a big if, because let's say you have a very big energy storage system with a battery, right? So if it degrades, let's say you buy a new phone, right? Nowadays, I don't know if other phones have it, but iOS, they show your battery health, right? With time, they say as your cycle life increases, cycle life generally means the the times or the frequency. I should say frequency. 0 to 100% and back. So what does that mean? That is that if you charge from 0 to 100 and then come back from 100 to 0, so how that is considered as one cycle. So let's say you have an iPhone, you charge it till 100, you discharge it at 50, right? And then again charge it to 100. So for this, you'll take at least four times to do. If you do it four times, that will count as one battery. Sorry, that will count as one cycle. So that's why they generally ask you to just keep your phone, don't let it go below 40%. So we'll discuss more about how the cycle life. Just I'm just giving you an explanation what a cycle means and efficiency, right? So they have lesser. So efficiency generally means how much losses they incur while charging and discharging. So we'll discuss more on these aspects later. So I already told you they have ramp rate, high ramping rate. They can have better frequency control, voltage regulation because they are DC in nature. So you generally have an inverter. So inverter has MOSFET based switches. So if you control the firing angle of these MOSFET based these switches, you can control the output of reactive power from that in this inverter. And then transmission and distribution upgrade differ. So you can generally defer the amount of upgrade. That's it. I don't remember why I had this. Yeah, I guess I explained. Yeah. So this figure, this was taken from this New England ISO, which is an ISO or an independent system operator in USA. They have projected when they will due to the solar energy penetration, when will the grid become unstable, in which year? So they found out in 2024 there is a potential for grid instability with the growth, with the rate of growth they are experiencing with the solar based generation. So as you can see, during the solar times, what happens? Usually it starts forming a dip. Sorry, this dip may last till the solar hours are there. That is, till the daylight is there. When solar is generating power, this dip lasts. So you can see this dip has increased from, let's say, some 1200 megawatts to now, sorry, to now less, to now 500 megawatts. So this has gone down 700 megawatts, what they expected, right? So this is a huge ramping that is required. This is a huge ramp product that they require now because of this duck curve. So this is called duck curve because it's like a duck. So its curve is like a duck. So so this makes to be able to balance the load and generation at all times, you require huge. I should do this. You require a huge ramping product. So how will you get it? If you have renewable, there is no ramp product. I mean, you are just feeding it whatever you want. So in America, at least now, they consider all the generation as renewable generation as negative load. That is, feed whatever you are making will consider it as a negative load. So if you have a 250 megawatt of load and you generate 50 megawatt, they just say you have a 200 megawatt of load at that time. So if this is a negative load, your duck curve, your duck curve's belly is increasing, and if this belly is increasing, you need higher ramping products. So how will you get that ramping product? Your coal won't supply it. Your hydropower station is not there. I mean, if you don't have good flow of river, how will you make a hydropower station, right? So generally they are made in the run of the river. So I mean, if you can, this is a very costly phenomenon. So I'm talking about this dip, but what about this? The rise that you need is even more. So now they have started looking for things or for energy generations that will be able to survive this ramp. So which is generally found in battery energy storage systems. So yeah, so that's what I mean by when I say ramping. So you need to be able to switch your increase your generation fairly quickly in a limited amount of time to be able to maintain the load and generation balance. So now let's talk about a battery energy storage system and how does it look. Let's say you have, so as I told you, in order to use battery with grid, let's say this is grid, you need to have an inverter. What does an inverter do? Can anyone tell me? Arey yaar. So inverter, it converts DC to AC. So so when you have this in at the point of common coupling, you will have inverter losses. So this losses could be due to switching losses or other losses that are due to power electronic interfaces. Then you have some idling losses. So what do I mean by idling? Let's say that when you have a battery lying around, let's say your phone, it doesn't stay at that SOC for a very long time. It depletes even if you don't use it, even if you have switched it off. So this self depletion is generally termed as idling loss. Then there is a state. So this connection or this is a kind of a switch. This depends on the state of the system. So if you are charging, discharging, or idle, that's how the state will behave. This is an equivalent circuit model of what a battery energy storage system coupled with a grid would look like. Then you have charging or discharging losses. So when you charge, the amount of power you're taking from the grid doesn't generally come to your battery. So it's generally a lesser amount of energy that goes to your battery. Let's say if you're taking 100 kilowatt hours from the grid, and if you have 0.95% efficiency, only 95 kilowatt hour is coming to your battery, but you're paying for that 100 kilowatt hour. Similarly, when you are discharging, let's say if you're discharging around 100 kilowatt hour, then so you are discharging more to be able to come up with this 100. So how much you are discharging, this will come out to be around, I don't know, let me do it. Yeah, around 105 point something, right? So you are discharging more, but you are being paid only with for this 100 kilowatt of hour of energy that you have given to the grid. So that's how it will look like. And the stored energy is generally represented with ET. I'll show the whole the mathematical equations too, but let's say that this is how the stored energy will look like. This is all the how the electrical side of it will look like for a battery that is coupled with the grid through an inverter. So let's talk about the mathematical model. So let me give you. So ET is what? Energy in the battery at time t. And if you want to talk about ET plus 1, that is at the next time instant, this will be a function of how much you have charged or discharged, right? So it would be ET, sorry, minus delta t because you generally have power, and it would be PDT. So a charging or discharging efficiency can be different. Right now, I'm just taking clubbing them both as same, that is eta, but they can be different. Correct. So that's how your mathematical model will look like. That's how the increment of your battery storage will be. So this will be with the decision variable. So if I do this, I must do it like this as well. UD, UC, couple it with the unit commitment variable. So What does this UD and UC specify? That at any given point of time, your battery must either be charging or discharging. It can't do both. So if both of them will be one, this equation won't be satisfied because 2 is not less than equal to 1. Both of them can be 0. They can be at idle position, but cannot be 1 at the same time. So you just have to multiply UD with PD. And you also take this assumption. So let's say if you are charging your battery and discharging it, so when you solve it through a this mathematical model, so if you, for sake of simplicity, for sake of uh, brevity, people generally do it that at whatever time instant they are, from 24 hours from now, they will be at the same battery energy storage. They'll be at the same energy in the battery, because it's easier to solve the problem. Otherwise, if it starts going up and down, the whole mathematical side of it will become difficult to solve. So we generally do it like this. If the battery during the initial stage, which is E11, is equal to the 24 hours from now, which is T1, which is equal to T rated by 2, right? And then we specify one more quantity, that is your state of charge. So what is state of charge? SOC, it's nothing but E upon E rated. So I should say ET. So energy at any time instant T in your battery divided by the rated capacity will give you the, I don't know why my screen is going off. Yeah, battery at any time T will give you the SOC, let's say 50%. So if your battery can store 100 kilowatt hour, it's at 50 kilowatt hour right now. That is what is stored in the battery. Then you have depth of discharge. This is an important quantity. This is nothing but 1 minus SOC. We usually use it when we are performing analysis on this degradation cost. That's where you will see it most, which is just 1 minus SOC. So now you know the mathematical model of your battery. So you will be interested to know how the equivalent circuit model will look like, right? So generally in the literature, we generally represent it with capacitors and resistances with several time constants. So generally in RC, which is a resistor in parallel with capacitor, is generally called as a time constant. So this is a 2 RC model or a two time step time constant model. We can have NRC. So this generally models the transient behavior of the battery, how the transients in your battery will behave. So the higher the number of this time constants, the better will be the transient behavior that you can get from your battery. Right. For the sake of simplicity here right now, I am just showing a 2 RC model, or I have written it as N. So you can just say that it's an NRC model. So this sorry, this R self discharge generally is the when your battery is not functioning, if it's switch off, this whole part of it is cut off, the second side of it. So the loss which is happening in the battery, that is due to the self discharge loss of the battery. OC is generally the open circuit voltage, that is how much of power it can supply at any given point of time. As you can see, it is a dependent, it's a dependent source. It depends on a particular quantity. Generally, it's the SOC on which the your open circuit depends. So as you will see later on, you will see your SOC versus OVC graph. Oh, sorry, VOC graph. So your SOC to get so how is your SOC determined? It is usually determined on how your VOC is changing. So this is how your equivalent circuit model will look like. So I request you to go through the lecture material available on the website. So in this 2 hour lecture, I can't cover everything. So I have left the analysis part, that is the mathematical side of it, for you. It's beautifully explained by Professor N.P. Padhy. If even if you don't have time, just make sure that you go through the PPTs that are given at the end of the lecture. So that will be very helpful. I would like to add this disclaimer. I haven't done for this class that in no way these classes are the substitute of your weekly lectures. I would request you to please follow them to be able to follow these lectures beautifully. Yeah, so SOC versus DOD is nothing but That's what I said. 1 minus SOC, the amount of uh, discharge that your battery goes through is how your DOD is classified as, which is 1 minus SOC. So this small picture will give you. So can anyone tell me? I will leave this statement with you. I want you to go through it. Why lesser DOD? That is, um, so so please remind me in the next week. We'll discuss about it. But I want you to go through it. So I'll just leave this statement right here. This question right here. That why lesser DOD is detrimental for your batteries. That is, if you let's say just use your battery for 20%, 100 to 80. So is it beneficial or not? So I am just giving you the fact that it's not beneficial. Just give me the reasons why it's not beneficial. So we'll discuss more on this in the next time we meet. Yeah. So that's how this whole thing would look like. So I want to talk about two things: the battery degradation explained, because this is a major component. So as you know, with EVs, if you would have looked, you can check Tesla's website. So they have given that. If you let's say your battery is discharging very vigorously or very fastly, it's getting to 0% very quickly. So what's happening is basically your battery has degraded. That is, if it was offering let's say 100 kilowatt hours when you had it for the first time, now it will only be giving you 25 kilowatt hours. So that it's storing only 25 kilowatt hours of battery. That's why you're going through the cycle quickly. So this degradation, so generally this batteries are very costly, so that's why people generally have a very timely schedule of charging the batteries. Even Apple has this battery health feature where it stops charging your battery. It doesn't to stop overcharging your battery. What it does is it charges it at a very fast pace till the 80%, and then it trickle charges that it charges it very slowly for the next 20%, so that by the time you wake up from your sleep, it will your phone will be charged. Otherwise, if it's charging, if it let's say you wake up at 6 a.m. and if it has 100% at 2 a.m., for the next 4 hours it will overcharge your battery. That is detrimental for your battery. So this degradation, generally people are trying to come up with ways to be able to lower their total battery degradation over the whole life cycle. So generally, a Tesla car, that's what I was talking about. The battery is very costly. It comes out to be it is at a break even with the price of the car. So when you go for let's say you want to reinstall a battery because your battery has degraded, the price would be the same of getting a new car. So why is this? I don't know, but generally lithium ion is a very costly battery. That's why. So this battery degradation, we generally have two kinds of it. It's calendar aging, and writing is very bad. It's calendar aging, and then there is another side of it, which is cycle aging. That's what we talked about before. So both have different meanings. So basically, an aging is that it's due to um, due to the whole life of the battery, due to a very large amount of time it is with you, with temperature, humidity, DOD, and a large number of charge or discharge cycles. What happens? The battery usually forms cracks. These are cracks in the material that is used to make your battery. What these cracks do? This leads to a lesser amount of how much energy they can store in the battery, right? So these crack formation is what is producing battery degradation in your batteries. So we generally have two kinds of it. It is calendar aging and cycle aging. Calendar aging is generally the inherent aging, which is due to various factors, which is generally over a period of time. While cycle aging, dependent on temperature, depth of discharge, and other things, this is the total life that it loses. So, due to Good evening. I request you to please discuss some questions related to third assignment so that it will help us to solve third assignment. This is week 3, right? Yeah, I'll do that. We have 2 hours, right? So I have to first go through the whole material. I don't know if you know it. I told you for first hour I'll discuss everything. In the next hour we'll discuss questions. So don't worry, we'll go through it. That's what we have been doing for the past 2 weeks, right? You are always joining the call as well. So yeah. So life lost. Yeah, each time it goes through a cycle. Right. So I have to take this class for 2 hours. I mean, the NPTEL monitors it that we have to upload a whole 2 hour lecture. We can be a bit minutes off. I mean, that's not a huge problem, but I can't take a class only for an hour or for 1 hour or 30 minutes. So to suffice the time, I've divided it into 2 classes because it's MCQs, right? It's just facts that you have to answer whether they are true or false or if what a for certain fact means. So that generally takes less than 30 minutes. So if to in order to prolong that, I can discuss a brief summary. You can ask questions, but you never answer. So nobody answers my questions as well. Nobody asks out. So I have to go through the whole material as well. So yeah, these are the two kinds of degradation that the battery goes through. And yeah, 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 Krishna, you're saying? Hello? I guess it was a misclick from his end. Yeah. So that's what generally is meant by battery. So now, Krishna, your mic is on. I would request you to please kindly mute it. Otherwise, if you have question, you can ask it.
Batting Lala.
Krishna. Okay, so let's go ahead. So so in order to so you need to properly able to optimally allocate a size of the battery energy storage system. You can't just come up with 100 MWh of a plant where you don't even require it. So that's where you lose your investment. So to be able to optimally site and size the location, size the total battery energy storage system that you require, you generally go through an optimization problem. So I guess you all are comfortable with optimization problems. These are generally an objective. Let's say you have a minimization function of some fx. You have some constraint which generally are first inequality constraint and some in inequality constraints. You generally solve it using this is an optimization problem. You generally solve it using Lagrangian methods or other heuristics or uh, other mathematical approaches. So an ESS allocation also goes through a similar optimization problem. Sir has explained a 33 bus 33 bus system for this whole allocation optimization problem. I would request you to go through that lecture. I guess it's the fourth lecture, and you'll be able to appreciate what these will be, but still I'll go through some points of it. So first you need to identify the application of it. Until and unless you know what the application of the ESS is going to be, you won't be able to come up with how much storage you will require, right? Then you would have to formulate it as an optimization problem to determine the size and location of ESS, satisfying the technical and economical constraints. So what it requires network information. So network information is usually used for the power balance constraints or the power flow constraints. And then the ESS and the cost parameters. The output is generally the optimal operation serving the chosen application. So that's what you get out of the whole optimization problem. So for ESS, an objective could be minimization of investment, operation cost, the power loss, or the voltage deviation. The constraints are your power flow constraints, ESS ke operation constraints, which are the mathematical model which I have discussed over here. This is also a constraint, and upper and lower bounds on decision variables. And you have to then identify what kind of method you would require based on the pros and cons associated with each method, and then you validate it on a practical set with a test or a real system, and then you can come up with it. Here I will just give you a brief overview of this. So let's say so you can have integers or continuous variables as your decision making variable. So let's say if you are making some variable with respect to cost, where your cost is a function, let's say fx, I'll be like this, fx, where x is your total generation, it's a function of cost, that is ax square plus bx plus c. This is a quadratic function associated with cost, and x can be a continuous variable, right? You can supply from anywhere between the upper bound of the variable and the lower bound of it area. Lower bound is generally 0 or 10, 0 or some number below which the operation is not possible. So you use it as an objective to minimize the total cost of running that system, where the decision variable is generally the generation associated with it. So this is a continuous variable, and each of your constraints can either be linear. Your objective function and your constraints can either be linear or non-linear. So if it's linear, then it's a linear programming problem. If it's non-linear, it's a non-linear programming problem. If all of your variables are of integer type, it's called integer linear programming. But if it's your the whole your set of decision variables can have continuous as well as integers, it's generally called either a mixed integer linear programming or a mixed integer nonlinear programming, given the fact that how your objective function and your constraints are, either they can be linear or nonlinear. So that's how you usually classify it. If you see for a distribution system, usually the planning problem, it has this power flow constraints, right? The power flow constraints are usually AC constraints, which are generally non-linear. You tend to use some linearization techniques to make it a linear problem. But if you want to solve it wholly solely using AC based power flow, like you must have known this Newton-Raphson load flow, or the other kinds of load flow. So these are generally non-linear. So to be able to solve them, it's a mixed integer non-linear programming for your distribution system. So depending on how your constraints are or how your objective function is, you can classify it between non-linear and linear programming. Generally speaking, non-linear programming is harder to solve. Mixed integer non-linear programming, while as a mixed integer linear programming can be solved easily, you have freely available solvers as well. So that's all about optimization. So again, sir has given a whole class for it. So you have to go through week 4 to be able to appreciate this whole thing. Yeah. Next, how do you determine what kind of battery do you require? So here I've given how the size versus the weight of the battery goes to. That's the specific energy density versus the volumetric energy density, where lithium ion is at the top, and then it's a nickel and this I don't remember, but this is nickel, cadmium, and lead acid, where lithium ion generally has a higher energy density. That means it can store at a higher rate, uh, at a high value, high energy, and then it can discharge as well. Generally, nickel, cadmium, and lead acid usually had memory effect. Let's say if you were only using 20% of the battery, this memory effect will kick in. So the whole idea will be the battery will only store up until 20% of the whole design capacity of the battery. You can study more about how this memory effect is there in nickel cadmium battery. If you remember during the olden days when you had these smaller phones, the instruction usually came that you have to first discharge it and then charge it to a whole 100%, so that the battery knows what is 0% and 100% and it can recalibrate on its own. So that's what memory effect is. Lithium ion has zero memory effect. These are newer versions which are able to hedge the effect of memory. Right. And it finds use in many different applications: telecommunication, PV generation, bikes, EVs, street lighting system, UPS, wind generation, power tools. But for all, there are some advantages and disadvantages. So I request you to go through them. So they have they are the lightest metal with high potential difference. They are commercially available. They have their cost is reducing day by day. If you go through it, their cost is lesser as what it was uh, uh, in the past. Then they have high energy and power density. They can store more power. They can store more energy, and they can discharge and charge easily and quickly. They have negligible self discharge, and then they have flexibility in different cell types. But they require monitoring and protection. So why do I see this? So if you could see in conditions which are humid or hot, which is, let's say, India, you must have seen EVs catching fire on road, right? You won't see this generally in countries which are not that hot and humid. Why does this happen? Is because of poor monitoring and protection of the battery. So I would request, who is this? Rajeshwari, your video is on. If you can just turn off your video. Y- Yeah. And then, yeah, so what I was, if they require monitoring and protection, that's where battery management system comes in. Then you have cost. They are not cheap yet. And technology is developing day by day. So let's say you had the technology 2 years back. Now the technology has changed. So in 2 years, your battery became old. So that's not what you want, right? To be able to sustain the growth, they are not currently being doing that because the technology is developing at a very high rate. They have aging, they have degradation. It's with all batteries, and they are prone to overcharge or discharge. That's what I was showing. So a BMS would help in greatly monitoring the usage of your battery and to be able to protect it from various different things. So what it does is it takes input as voltage, temperature, and current. It has a control algorithm. It can be of various different types I'll discuss. And it can tell what the SOC of your battery is, what your state of the health is, and what is the fault or the status of your battery at any given point of time. So that's why usually you would have seen EVs catching fire. They generally blame it on BMS because BMS didn't kick in or didn't was not able to protect your battery from the negative conditions that the environment posed. So for this, you have SOC estimation or SOH estimation, which you usually have a conventional mathematical programming based. Kalman filtering is nothing but it estimates state of a linear system using noisy measurements. So it measures noise from the estimates, and then it gives you a state based on a linear. Sorry, it measures noise from your measurements and gives you a state of the system. So that's what Kalman filtering is. Then you have machine learning and deep learning. So deep learning usually you have seen in recent times you use a artificial neural network or different deep neural networks. They are generally used to be able to determine the functional relation between your inputs and outputs. So they generally approximate this function and tell you what the function is, so that you don't have you just give it a set of variable set of values, and it will give you the output of that set inputs. So main role of this BMS is to do cell balancing. Let's say if your battery is generally is called or has a pack of cells. That is, they have different number of cells, usually used in series, so that it is able to give you power. Let's say they are different kinds of cells, so they are generally clubbed to form a whole battery. So let's say your cell is discharging fast and quickly. So once it came to 0%, your SOC will show zero, but you still have energy in your different cells. So this is wasted, right? So you don't. So there's no use of having different kinds of cells to be able to protect your battery side, right? If one cell of your battery is charging or discharging faster, and let's say due to this, what happens? The other cell charges faster, and the next cell is usually not that it's not charged to the whole capacity, and it shows that SOC is at 100% here. So that's where you need cell balancing. This is generally used with so there are two different kinds of method: active balancing and passive balancing. In passive balancing, you use resistors in parallel to your uh, cells, where the resistors kick in when determines that the open circuit voltage of cells are different, so that the energy is wasted on the resistors. But this is a wrong method because it produces heat, and heat is not good for your battery. And then you have active. These are power electronic based devices. So these kick in when the control input is given based on various different kinds. So I would request you to go through the fifth lecture to be able to get how many different kinds of active and passive these are. There is the LC type, resonant converter type, and other stuff. So it will be easier for you to gauge. Sir has also not covered in a deep way, but to be able to give you how these look, you should be able to go through that. So I gave you a brief summary of week 3, and in this week we discussed about energy storage systems, particularly battery energy storage systems, because that is what we are being in use right now, and that is what we will be using in the coming few years because of the whole renewable energy penetration. But still, even though with benefits, they come with several caveats that we need to fill. That is, they have degradation, and they generally have balancing issues. And how we are doing that is what it's through proper monitoring and protection. So that is through BMS, and that's where BMS plays a role. So that's all for week 5. Let's go on to discuss some MCQs based on week 3 and on week 5. Yeah. So week 3 based system. So let's start with these questions. So these questions have topics covered not just from this lecture, but also from sir's lecture. So I will request you to, if you have gone through those lectures, please answer this with me. So the first question is, which of the following is not a type of mechanical energy storage system? So in a mechanical energy storage system, you generally use mechanical devices such as rotating masses or other mechanical systems. So can anyone tell me, out of all these, which won't have it? So this is latent heat. So this was given to us by NPTEL. So yeah. So can anyone tell me, out of all these, which one is not a mechanical energy based storage system? Yeah, Dharmendra ji. So you wanted me to discuss some questions related to third assignment, right? So I've given you names, right? So a compressed air generally uses. So this is the kind of a mechanical energy storage device. Yes, Krishna told latent. Latent is the correct answer. So compressed air uses what? It compresses the air so that pressure is built up between the medium, so that once it's released, the pressure would be used to convert the to is used as a means of generating in a is converting the kinetic energy that is available in the molecules of that compressed air to any other form of energy. Generally, it's electrical energy that we're concerned with. Gravity based, it's pulley mechanism. Let's say you have it's hydro storage, right? It's gravity based only. What you're doing, you're converting the potential energy of the water in the reservoir into kinetic energy by flowing it through small radius of pistons, so that they quickly come down and then they hit the turbine, and then the kinetic energy of the water is converted to electrical energy. And pumped hydro also works on the same place. It's just that it pumps back water back to the reservoirs as well. So, but latent heat, which is usually a type of chemical energy storage, is not a mechanical energy storage system. Next, which of the following combinations of energy storage technologies are not feasible for hybrid energy storage system? So, let's see if someone can tell me. I mean, all of them are hybrid, right? So, which of these will not be an hybrid energy storage system?
So I think a supercapacitor and battery.
No, they can be. I mean, you can have different types of storage systems, right? You can have a supercapacitor, you can have a battery as well. I mean, there's no point you can't have both. So it's kind of a trick question. The answer is none of these. All of them can be used as hybrid energy storage systems. There's no point of not having different kinds of storage systems. You can have all of them, but just use it at you don't connect them interlink. You don't interlink them. Just use it at separate things. You can have hybrid energy storage systems as well. Then can you solve this? Can you match the type of energy storage? So in the alphabetical sequenced uh, category, you have the kind of energy storage system, and in the numbered sequences you have the name of that storage system. So can you relate them if anyone can do it? C, someone's told C. Two people told, right? One told C. Okay, so let's do it. So what is a flywheel? So flywheel is mechanical, right? So this is 3 for sure. So you can eliminate this and this. Then you have battery. So what is battery? So can anyone tell me what is battery? So battery is what? Chemical, right? It's a chemical composition of the various different compounds. So it's sorry, yeah. And then fuel cell is electrochemical. Oh, sorry, I should say like this. Three. Sorry. Yeah. And then superconducting is electromagnetic. So if you can do it, then it becomes D4, electrochemical C3, mechanical 1, and no, sorry, A3. I was wrong. Sorry. It's chemical, right? Fuel cell is all chemical because it's how the electrolyte you place it and it converts it into water and electricity. Battery is electrochemical. Hmm. Hmm. And C2. So you have A3, B1, C2, D4. This one, right? No. A3, B1, C2, D4. So your third one is correct. Yeah, C is the correct answer. Next, which of the following storage type has high energy density? Can anyone tell me? Is it A3, B1?
lithium ion.
Okay. Yeah, lithium ion. Yes. So flywheel can only support whatever its inertia will tell it to, and then supercapacitor, you would need a very large capacitor. I mean supercapacitor to be able to match the energy density of a small lithium-ion battery. And lead acid battery, I have already told you its volumetric energy density as well as its geometrical energy density is nowhere near to what the lithium-ion is. So the answer is lithium-ion. Okay, can anyone solve this question? A 12-volt battery with a capacity of 500 ampere is at 80% SOC. Find the DOD, depth of discharge. It's easy, right? What do you do? DOD is 1 minus SOC. So it's simple, 20%. Correct? So you have easy questions, I guess, in the assignment as well. So next question. If a 12-volt battery has a capacity of 500 ampere hour, which is at 80% SOC, what is the amount of energy stored in that right now? So at 100%, it can store 500 ampere hour. How much can it store at 80%? Okay, 400. I got one for 400. Anyone else? 400. Correct. So it has 20% DOD. So that means it has used its 100 ampere hour of battery. So that means it's left with what? 400 ampere hour. Next, I remember telling you. So can anyone repeat if someone followed my lecture? So a distribution network planning problem is what kind of problem? So I will repeat it if someone wants me to repeat it. But I told you in the class why it's what kind of a problem. Can anyone tell me? Hmm. Okay, yeah. So I told in the class it's mixed integer nonlinear programming. Let me tell you why again. So a linear programming has linear constraints as well as linear objective function. But a non-linear programming, even if there is one single constraint or if the objective function is non-linear and the rest of the constraints are linear, even if one function is non-linear, the whole problem becomes non-linear programming. And what do I mean by mixed integer and integer based? If let's say you have continuous decision variables, that is if you are trying to find out the optimum generation so that your cost will minimize, then it's a continuous decision variable. Your problem becomes mixed integer because you have a continuous decision variable, right? So it is a mixed integer variable. It will become a mixed integer programming. And why distribution network planning problem is mixed integer? It's because of power flow constraints. So power flow constraints are generally, if you don't linearize them, I'm telling again, if you don't linearize them, so how do you do it? You when you have AC constraints and DC constraints, you linearize them. You have that voltage doesn't deviate much, reactive power is available abundantly. So that's how you and then uh, uh, yeah, and you don't have a reactive power flow in the lines, and that's how you come up with real set of optimal power real set of constraints. They're generally called as DC power flow. But if you use an AC power flow problem, it becomes mixed integer nonlinear programming because these are nonlinear in nature. So I guess you know what is a linear function or a nonlinear function. Can anyone tell me if someone doesn't have an idea of what a linear function is or what a nonlinear function is? So please tell me if you don't know it. So I'll take some things as I can assume some things about it, right? That you don't know that you know about it, but if you don't know about it, I'll be happy to explain. When is a function fx called a linear? Anyone?
It follows the superposition, linearity, and homogeneity.
Yeah. So yeah, you can tell it, but in simpler terms, if you can represent it, so that is a definition of a linear system. So I would request you to check if function and system are yeah, it's a degree one. Any polynomial with degree one is a linear system, a linear function. That is if you can plot it like a straight line. So Dharmendra Kumar. So if I say if a system is y is equals to 2x plus 1, will it be a linear system or a non-linear system? It's a linear function, but
Yes,
will it be it will be a non-linear system, right? 2x
yes, sir.
plus a constant. Yeah, because it doesn't follow what principle? Homogeneity or what principle doesn't it follow? It doesn't follow both of them. So linearity property is not there. It doesn't follow homogeneity. So the that system is not linear. But here I'm talking about a function. So a function is the polynomial with the degree one. That is, if you can plot it with a straight line. So if you have nonlinear set of constraints or even one function is nonlinear, your whole problem becomes nonlinear programming, and that is why the distribution network planning problem is mixed integer nonlinear programming. Yeah. So for a mathematical programming approach, if someone has gone through the lecture, can anyone help me with this? Yeah. Anyone? No one. So generally, yeah, someone was going to say.
Yes, sir. I think low computation burden and short convergence time. Simple formulation.
No. So the advantage is, so what you refer to were the disadvantages. Uh, it doesn't have a low competition burden. So for a mathematical programming approach, you have a higher competition. So you generally don't have it, like you won't get a perfect. So it's not too high. I mean, as high as the heuristic approaches, that is artificial intelligence, but still there is a computational burden. You generally, what you do for nonlinear programming, you generally tend to linearize it so that the computation burden is removed some at some level, right? So computation burden is there. Conversion times is not short. If I give you a nonlinear programming problem, the convergence time won't be short. That's for sure. Formulation for a nonlinear programming won't be simple. It's that for a mathematical programming approach, if you solve mixed integer nonlinear programming with a good solver, or if you use mixed integer linear programming with a solver like Cplex or Gurobi, you will get global optimal solution. That's not guaranteed in any other approaches. A deep learning approach doesn't offer global optimal solution. I mean, it may or may not offer you a global optimal solution, and it has a higher computation burden as well. But the same does not exist with a mathematical or programming approach. Whatever your answer will be, it will be global optimal. That's for sure. But for the rest of it, you can't say with clear distinction. Okay, yeah, I didn't talk about this in my lecture, but can anyone tell me what is the direct cause of permanent failure of lithium ion? I'll just tell it because it's not really relevant. But if someone wants to talk about it, you can watch Sir's fifth uh, lecture slide. So a direct cause is due to damage to the SEI layer, which is generally called the solid electrolytic interface layer. So your battery generally has a medium, and with medium it comes with it has contacts, and that's an SEI layer. So if it damages, there is no point. Your battery is at a permanent failure. So next question: the indication of SOC is best given by. So not the temperature, not even the color of electrolyte, not even the level. It's the specific gravity of the electrolyte. You can watch Sir's lecture; he has explained it. So in a 2 hour lecture, I can't cover 5 hours of lectures. That's impossible. But yeah, you can watch it. So next question. So according to storage development deployment statistics released by the US DOE, which of the following is correct to India? P, pumped hydro storage has the highest share of total storage, and thermal storage is greater than electrochemical and electromechanical storage, combined storage. Can anyone tell me which one is correct? Yeah, let's comment at the end. I mean, it's something that I didn't cover. So third question: which of the following depicts the need of energy storage in power grid system operation? Yeah, this I covered in depth. If anyone can tell me
Sir, what is
which
the
of the
answer?
following. Second,
Yes, sir.
it would be one and two. So pumped hydro storage has the higher amount of storage as of now. Battery energy storage is at a nascent stage, and thermal storage is much higher than electrochemical and electromechanical combined storage, because thermal storage is what it's how you store your thermal power, and then you power your coal based power plants, right? It's a combined heat and power plant. So it's one and two. It's the correct option. So it's in Sir's first lecture, I guess, where he has discussed about a roadmap for Indian evolution. So you can check it. So this is given to me from NPTEL team. So I'm just discussing it with you. Third question I covered in depth today. So if anyone can tell me. So with database questions, I don't expect you to answer all of them because these are database question. Okay. I mean, you can, some numbers you can have at the tip of your tongue, like what is the projected solar capacity by 2030. But not all data I want you to be having at your tip of your tongue, because it doesn't matter. But yeah, you should be able to relate what exactly we are studying and why exactly we are studying. That's where I majorly focus. I have to discuss all of these questions because these are given to us directly from the NPTEL team. But yeah, third question, it's directly relevant. So can anyone tell me? So for which of the following depicts the need for energy storage in power grid system operation? Is it black start services, reduce in renewable energy curtailment, capacity investment deferral, or frequency regulation and flexible ramping? Anyone?
Sir,
If
first
I
option.
talk,
First.
yeah, yeah, 1 and 4. From a system operation, what we require? We require ancillary services that are support services. So that is black start services and frequent and other services that we can get out from BESS, and we require it to regulate the frequency and provide ramping reserve. That's what we require from the system operation perspective. From economical perspective, we do require to reduce the curtailment of the renewable energy and capacity investment deferral, but those are not from the power system grid operation point of view. Fourth question, which of the following matches is false? It's based on characterizing these different systems. So who can tell me the answer of it? So which one of the following matches is false? Pumped hydro is so a pumped hydro, they are classifying it as hybrid energy storage system. Is it true or false?
The question is not visible clearly. Option. All options are not visible clear.
Oh, so is it the same? So is it with my connection or yours? Because I can see my
No,
screen on my
actually,
laptop.
only two options are showing. Yeah,
I'm
no,
I'm
no,
talking about fourth.
yes.
I'm talking about fourth question. This question.
Okay, okay, sorry.
Yeah, yeah, yeah. So can anyone tell me if the first match is correct or wrong? So a pumped hydro storage, is it a hybrid energy storage system?
Yes, sir.
No, it's a false statement, right? It's a mechanical energy storage system. So this is the statement which is false. So the answer is one. I don't know if you're talking wrong or correct. Yeah, one wrong. Yes, yes. So the first statement is incorrect. Let's go through next as well. Lead acid is lead acid is electrochemical. Then biofuel is chemical, and battery and flywheel are hybrid energy storage system. So one is incorrect, which is the answer. So fifth one. Can anyone tell me which storage technology has a very good usable capacity?
Uh, Supercapacitor.
Supercapacitor, how can it have a very good usable capacity? So supercapacitor, you require a very big supercapacitor. Could let's say if you have a very good supercapacitor, it can sustain about um I don't know the exact number, but in the range of kilowatts. But it's not the same with the lithium ion battery, right? You can have multiple different batteries interconnected to it to increase the whole overall picture. So the usable capacity is with lithium ion. So you can extract maximum benefit out of a lithium ion battery. Yeah, the correct answer is lithium ion. Shweta has answered. So which one of the following storage capacity technology has not so good cycle life? So if we talk about cycle life, it's the total cycles it can withstand before it degrades. So which of the following has not so good cycle life? So let's talk about it. Flywheel, we don't generally talk about cycle life. It's based on depth of discharge and state of charge. Supercapacitor as well, because supercapacitor, what is it? It stores energy in it as an electric field. So it uses it by displacing charges to the different plates. But a redox flow battery doesn't. It's still better than lead acid based battery. So the lead acid battery has the least cycle life. So why? Because of just a second. So why? It's usually because of memory effect. Again, I'll just add it. So please go through it to be able to figure out what is memory effect. So I talked about it, the memory effect. I request you to go through it as well. So what is a minor complexity is a significant advantage of which battery modeling methods? So we talked about like equivalent circuit model, and then we talked about what is an empirical battery modeling model and what is electrochemical. So electrochemical, usually we model how the battery will look like and how the chemical composition of it. Equivalent circle, we model it as time constants or RC based, and then empirical, we used both. So which has complexity, which is a significant advantage for the battery modeling model. If we use both, right? So empirical based methods have a high significant advantage. I mean, please go through the sir's lecture. I mean, my whole lecture won't suffice all of these questions. 8. Which is the disadvantage of the lithium ion battery? We discussed it. So here is the disadvantages. You can go through it once and then we can go through the question. So which of the following is the disadvantage of lithium ion battery?
I think, sir, degradation effect.
Yeah. So degradation effect is usually what is the disadvantage of it? High potential difference in self discharge rate is not a disadvantage with the lithium ion battery. So ninth question. Suppose the objective function of an optimization problem is convex, then which of the following is true regarding the overall optimization problem? Non-linear constraints always result in a non-convex problem. Linear constraints always result in a convex problems. Linear constraints may result in a non-convex optimization problem, and non-linear constraints may result in a non-convex optimization problem. I mean, sir didn't also cover it, and I also didn't cover it. So let me tell you what is convex and what is non-convex function. So for a convex function, if let's say your function is like this, a circle, right? The whole function will be non-linear in nature. But if you can have a line in between this function which does not cut the whole plane, a line joining any point A to any point B, which doesn't cut the plane or which doesn't exclude the plane, the function is generally called convex function. But what if you have something like this? So if I draw a line between this, it cuts the whole function, right? So these kinds of functions are called concave functions. So problems are not generally done for concave functions because they can't be solved using the optimization problems as of now. So we generally convexify them. We convert the concave function to a convex function like this. So instead of modeling it as the red one, we model it as the green one. We convexify it to be able to solve the problem. So this is what is meant by concave and convex functions. So it's saying non-linear constraints always result in a non-convex problem. I told you a circle, an equation of circle or function of circle is generally non-linear, but it is a convex function, right? So you can't always say that it will always result in non-convex function. So this is a false statement. Linear constraints always result in a convex optimization problem. This is true. A linear constraint is always convex because it's a straight line. So you can draw a line and it can be a straight line as well. Linear constraints may result in a non-convex problem. This is wrong. A linear constraint can never result in a non-convex. Third one. And non-linear constraints may result in a non-convex optimization problem. This is true. This red function is a concave function, and it is a nonlinear function, but it has resulted in a concave function. So the answer is 1, 2, and 4, which is B. So does anyone have problem? So do all of you get what is a concave and what is a convex function, or do I repeat it again? So it's a function in on the graph. If you can draw a line which only passes through, which does not cut the plane of the function or the plot, it is called as a convex function. But if it does, it's generally connoted as a concave function. So any difficulty with concave, convex, a thumbs up or a thumbs down, I can explain it again. Yeah. So this was not covered by sir. So I thought of covering it in the question itself. Last, which is or are the significant advantages of the hybrid algorithms estimating battery SOC? So to estimate SOC, you have conventional mathematical methods, and then you have adaptive Kalman filtering. I explained what is Kalman filtering. Then you have machine learning, and then you have deep learning. But you can have multiple hybrid of these as well. You can have Kalman filtering with deep learning methods as well. So you can take best of both worlds to be able to get better results. So on similar lines, can anyone tell me what is or are the significant advantages of the hybrid algorithms estimating battery SOC? So they can be more effective, right? You can combine the characteristics of both of these two different kinds of, yeah, it's the both of these two different kinds of uh, algorithms to be able to get best of both worlds. You can do it with higher precision. It could so be that your conventional method has 70%, right? Or your Kalman filtering has 70%, but your deep learning has 80%. But combination of them, you can have 85%. So you can get a higher precision from that, and they can be reliable as well. So the correct answer is all of the above. So this is all for the MCQ. So today we discussed energy storage systems. Specifically, we dealt into why we need energy storage systems, how coupling them would with the grid currently could help us alleviate some of the problems that I mentioned. Then how are they different from system operations and other aspects? Then we talked about various different types of terminologies associated with that, how a load curve is changing, and how battery energy storage system could help sustain the continual balance of these two things. Then what is an equivalent model of it? How do we model it? SOC, DOD, the terminologies, the mathematical model of it. And then we went into degradation and optimization problem, which is the how to allocate energy storage system and the kind of battery and what are the uses of it and advantages and disadvantages. Why do we require BMS? I told you, so to be able to monitor it correctly, we need a battery management system. So let's say in India, I told you, right, EVs are catching fire. Why? Because of a faulty BMS. And balancing, why do we need balancing? And we discussed some questions. So if anyone has any doubts, please come forward. We have 10 minutes, I mean, so we can discuss doubts. Dharmendra ji, do you have any doubts? So I know questions are a bit, these are objective questions and based on,
Sir, thank you.
uh, yeah. So these are objective questions and based directly on one or two sentences from the whole week's lecture, right? So there's nothing I can do with that. I mean, these are the previous year NPTEL questions, so we are just taking from there. And when I find the need of it, I make my own questions as well. But I didn't find the need today because we had 20 questions. So I thought they will suffice. But yeah, some of them are direct. They are taken directly from the instructor's lecture. So that's why I tell you. So there's these lectures that I give you a brief review. These generally won't suffice. So you would have to go through all of those lectures to be able to answer the questions in the assignment as well as in the sample problem solving session as well. But yeah, I try to explain questions when they are there. But if they are based on data, I can't do anything. That is what the data is, right? So if there is a Department of Energy release statistics, we have to answer based on that, right? I can't explain data, but I do explain when I find the chance of explaining. Like, I hope you find my explanation easy to understand. If you have doubts, please come forward. Any of you?
Hello, sir.
Yeah.
Sir, we have renewable energy sources. So in the market perspective, these are very cheap generating units. Okay, but why we are trying to integrate battery storages? Even they have
Okay.
large
So
costly. They
what
are
kind of
costly.
what kind of renewable energy resources are cheaper? I mean, can you quantify in what markets they are cheaper?
No. I am generally talking about solar or wind energy.
Yeah. So we can't say they are cheaper, right? Their market-based participation is not explored fully. So if I told you, that's why I told you, in US right now, let's say they are considered as negative load. We don't have a market for them. In India, we do have green day-ahead market, but we have a separate market because we are trying to force distribution utilities to have a certain obligation, right? They have renewable purchase obligations. So to fulfill them, we generally have a separate market. But these are not cheaper. I mean, solar has now sometimes in Gujarat has become cheaper. It was around 4 kilo rupees 4 kilo per rupees 4 per kilowatt hour. But these are not too cheaper as other fossil fuel based approaches. But yes, your point is right. Even if they are integrating them with BSS will make them even more expensive, right? But let's talk about lost load opportunities. Let's say uh, due to this duck curve, you have a high ramping rate, and sometimes your system operator is not able to continually balance them. So what happens? You have cut brownouts. That is, your power is usually cut off, or your load is usually curtailed for a period of time. Or what can happen is you can sometimes use expensive resources to balance out these curves. So system operator is paying a price for it, right? So why not have a battery energy storage system to form these renewable energy sources, so that something like this doesn't come into picture, so that you don't have load curtailments, you don't have brownouts, you even don't have blackouts due to ramping rates, and your load and supply is generally is continually balanced as well. So from a system operator's point of view, it is lucrative. Yeah, but it's not. It's still investment. It still is expensive in investment. So that's true. But yeah, the benefits that is posed severely what you say are much more than what are the disadvantages associated with that. So that's why I told you, right? With the growing time, let's say this is for 2024. What about 2027? Let's say the load touches zero for some time due to the negative load. How will your generation suffice that? Also, for that, you would need a battery energy storage system. Yes, Dharmendra ji.
Yes, sir. One question, sir.
Mhm.
What is the active cell balancing? What are the different methods?
Okay. So I talked about passive cell balancing. So what is done is you usually employ resistors, so the cells with the higher VOC, the uh, open circuit voltage, they generally what they will do is they will um, 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 dissipate power in these resistors. So these have heating effect. So what happens is due to this heating effect, it poses additional disadvantages to the cells. So what you do active switching. So what you do, you have switches with the cells, and these switches are in turn connected with, let's say, another set of resistors or some transformer based sources which can dissipate power from these cells. So what happens is you turn on these switches when the VOC is different from rest of these cells, so that the excess of energy is dissipated on the different sources that have combined. So what it does is it minimizes the amount of dissipation of heat that happens in your system. I mean, still the heat is there, but generally the switches will overcome that because they also have some losses in them as well, built in them as well. So that's where these would come into picture. These are generally power electronic devices which will help you in managing the capacity of the cells. So your if you can look at the lecture, you have different kinds of um, active cell balancing methods, such as uh, these resonant converters based methods, and then you have LC based method, and then you have different types of methods which are generally concerned with power electronic devices. So that's where you generally use them. So did I explain your doubt? I think I deviated. So this was your exact question, right? What are active balancing methods? I mean the
Yes.
hmm. Okay,
So
so
what are the key active cell balancing method?
yeah. So active cell, anything which has power electronic devices. Let's say you are controlling switches used on control inputs, right? So that's where this active comes into picture. Passive means you are just using resistors based on how the voltage deviation occurs. These resistors automatically dissipate power, excess of power from the cells. So these don't use control methods as such. They just generally pass it through the resistor so as to dissipate it as a heat. But active, they use another secondary component where they can transform this energy back to charge the some of the other cells as well. So that's where active cell balancing method comes into picture. Anything else?
No, sir. Thank you, sir. Thank you.
Anyone else? Any doubts? Can the recording be shared or the document? So I guess the recording and the document both are being shared with you regularly. So there is this problem solving session tab at the left hand of your screen when you open the course. So this tab, you can click on it. It will redirect you to a Google Sheet where you have access to all of the recorded lectures of different TAs that are taking this course. Any other doubt? Yeah. So
Hello,
before I
sir.
close any, yeah.
Yeah, sir, I got confused in difference between a linear system and linear functions. So could you please explain it again once more?
Okay. So a linear function or a linear. So when I talk about a function, when I say it's a linear, I usually tell when the polynomial that describes that function, or I should, instead of saying that, its degree is one. Let's say the polynomial has a degree of one, or we can draw it as a straight line. Plot it, I should say rather. So if I say y is equals to fx is a function based on x, and I can write it like this. So ax plus b, I can plot it with a straight line, right? Can I do that?
Yes,
Yes,
sir.
sir. Yes. Right.
Yeah. But with linear systems, you generally have a linearity property. Can anyone tell me what that linearity property is? It follows two different kinds of property.
Superposition and homogeneity.
So one is, I don't know, it's called homogeneity or homogeneity, and the other is, I guess it's additivity. Additivity.
Additivity, yes, sir. Superposition.
Yeah. So now tell me what is additivity and what is homogeneity.
Basically, if you give two different inputs and the
Mhm.
response individually.
Oh, okay. So someone else asked this question, right? So can anyone tell me what who asked this question? I forgot.
Sir, I asked.
Yeah,
So
yeah. So what is additivity?
additivity, as I know, if we provide two different inputs and their outputs also are the equivalent to their cumulative input. So,
Let's say we have x1 input. Let's say we have a function ax. We give x1 input, we get output y1 as ax1. And if we give x2 input, we have output as y2, which is ax2. So if I give a sum of these inputs, that is, if my input is x1 plus x2 now, so what will it become? So y will become a of x1 plus x2, which is y is what? Ax1 plus ax2, which is y1 plus y2. So this is a property of additivity. That is, it is the sum of inputs gives us the sum of outputs. What is homogeneity? Can you tell me?
Sir, I think if we are scaling the input, then such
Yes.
ratio, the output will
So
be
yes. So
scaled.
let's say, yeah. So let's say you are having let's say you give A1, your output comes as Y1, which is A1 and X1. You are giving the same input X1. But let's say you scale it with the, sorry, I should not do this like this. A, you will be confused, right? So let's say you gave a B scaling factor. So your output comes out to be what? For an X input, your output becomes Y of ABX, right? Sorry. Now let's say you give C. So your output is ACX, right? So this is what? This is Y1, this is Y2 for same input X. So this can be written as Y1 is equal to A time Y, or Y2 is equals to A time, sorry, C time Y. So you can scale it with different variables, but the output will still be a corresponding to your input that you're giving. So if the property, if they follow both of these properties, you will have a linear system. So let's say you have a system which is given by AX plus B. Can anyone tell me if it follows the property of additivity? I don't know if it's called additivity or additivity. So does it follow additivity? So if you can check, and does it follow homogeneity? So it won't. So this, if you scale it by the same input, the output won't be the same. And if you add the same inputs, the outputs will not be the cumulative sum of the outputs. So this function, even though it's linear, but as a system, it won't be a linear system. So if you have a constant with that linear function, your system won't be a linear function, linear system anymore, even though this function is linear. But not same is not applicable with y is equals to ax. The function is a linear function and the system is linear as well. So that is the difference between linear function and linear system. You just have the two properties that it should follow, which is additivity and homogeneity. So any doubts? So
No, sir. Thank you.
who asked? Yeah. So any other doubts if anyone has, or we'll close this meeting now.
So thank you, sir, for such nice session. Really, my doubt is cleared. And sir, next time when you will take the lecture, sir?
So I take it Saturday 6 to 8. So next Saturday 6 to 8. So I would request you to go through the lecture. So what happened last time as well when I was taking the fundamental of electrical engineering course. So in 2 hours covering five lectures is very difficult. So I have to miss out on some parts which are non-essential to the course. Like here I'm missing out the data. So I can't cover the data part because I need to cover the essential things that are relevant to your course, right? So that I expect you to cover so that you can answer the MCQs as well. So similar thing happened. People stopped watching the lectures and they just came directly to my problem solving sessions and they were unable to solve the questions as well. So I would request you to go through the lecture so that you can answer the MCQs as well as you can appreciate the problem solving session as well. So again, I would have to say that I have to take the whole 2 hours, right? So which is difficult if I don't cover give you a brief recap as well. So it's it's difficult for me because I can't get too many questions out of the whole course that for that week, right? It's an informative course. There are no what you say questions that I can derive like mathematical questions. So it's difficult for me to get questions as well. So I have to rely on what the NPTEL team is providing me, and I cover a thorough revision too. So please go through the lectures if you, and then come back to this lecture. You can watch it on YouTube as well. I upload it, and then you can appreciate the flow as well. So please don't judge in between that you are not getting anything. Just go through it as well. So that's all for today. So if there are no questions, I will like to end it. So all of you, I would request you to leave this meeting so that I can close it. Yeah. So thank you all for joining. Yeah, you're welcome. Thank you for joining as well. Yeah, yeah, welcome. Yeah, yeah, I'm closing this meeting, so I would request all of you to please leave. I don't have the host control, so I can't. Yeah. So bye bye.